Hello.
Welcome. If you're anyone joining the stream, if you're used to seeing a different face talking to you immediately, Brent's actually helping us behind the scenes today, but he's not actually on the stream with us. So I am running the stream for today, and we have some great information about multi-cluster Kubernetes and some possibilities on how to use it, like what sort of use cases you have, and some tools to be able to do that for you. So. I'm really excited. We have Adrian and Dimitri here. Why don't you, Adrian, go ahead and introduce yourself.
Yeah, so my name is Adrian. I'm the CEO and founder of Admiralty, which is a company behind the Admiralty open source project. And that project is used by Dimitri and his colleagues at UC San Diego and other universities to federate their clusters in a non-centralized way. Which is like what they were interested in. And I met Dimitri 2 years ago at KubeCon Seattle, and at the time I was just prototyping what was going to become Admiralty, and he was really influential in the design decisions along the way.
Yeah, that's great. And just a real quick, I'm sure it'll be asked at some point, and we'll get into a demo later, but how much of Admiralty is like overlaps with something like Cluster API that someone might be familiar with for, does it do the provisioning? Does it do the configuration of clusters, or what's the use case?
So Admiralty focuses on multi-cluster scheduling. Admiralty open source is a multi-cluster scheduler. It uses actually some of the frameworks and patterns of Kubernetes, like the scheduler framework and Virtual Kubelet, to do that. So it does not overlap with Cluster API. It's like bring your own clusters, and so while you provision your clusters, you'd install the Admiralty agent in each cluster like you would any other system, system components. And then you connect them together in any sort of topology. You can have a central cluster. You can have clusters talking to each other in some sort of decentralized federation, like Dimitri did. And and then Admiralty can take pods created in one cluster and actually run them in other clusters, and dependencies follow, and it works. And so we'll see how that works.
Awesome. And Dimitri, go ahead, introduce yourself and tell us kind of what you were trying to solve and why you landed with Admiralty.
Yeah, I'm Dimitri. I'm a software developer and probably DevOps now for UCSD. And this big project that I'm involved in is called Nautilus. Basically, now we're running a global Kubernetes cluster. And the project started interestingly. So there was a task of measuring the network performance between different universities. So there is what's called the Science DMZ network, which is pretty fast, like 10 to 100 gigabit per second network links between universities. And there is a task of making sure that those links are performing as they should, because scientists expect them to be 10 gig, but they are performing at, 100 megabits per second. And so we were deploying what's called Fiona node special servers in each campus, and basically they are just sending data and measuring the throughput. And at some point, that was all manual labor. And at some point, we just were overwhelmed with the number of those Fiona nodes and just manually configuring them. And we decided, we can throw just Kubernetes on them and automate those measurements. And that worked really well. You drop in another node and it automatically gets all the containers and starts measuring. So we were, cool. So now we have this orchestration system, which is just sometimes measuring network, but it's mostly sitting idle. And we started providing access to these Kubernetes clusters scientists. And at that point, we got exponential growth of it because it was super easy to onboard new scientists, and they were getting free resources because their campus is having this Fiona node, and they can use it for free and just run some containers on it and use for computations. And now we are, I think, hitting 200 nodes in different campuses in US, and also we have a couple nodes internationally. Like we have nodes in Korea, Australia, Guam, Hawaii, and Europe. And our cluster is still growing, but it's not possible to grow indefinitely. At some point, we need to federate. And there are a couple use cases. In some universities, they just want to manage their cluster themselves. So they want tight security. They have some like special requirements, stuff like that. Some clusters are working on some weird architectures, ARM, Windows, you name it, like some small like IoT devices, Internet of Things, stuff like that. And it's not easy to join them to our normal cluster, but we still want to run Kubernetes stuff on it because we like Kubernetes a lot. And we were looking for federation solutions. Actually, on that KubeCon Adrian was talking about, I was just looking at all the solutions, and they're all like, there is one cluster which is managing a bunch of other clusters, which didn't work for us because we want to collaborate with other universities. We don't want to manage them. And yeah, so I talked to Adrian, and Adrian got this idea. And so far, Admiralty is the only solution that allows us to federate on the same level with others. So we can manage our small clusters, our big cluster, and also federate with another universities and other groups that have their own Kubernetes cluster. And we are kind of influential in science, so we were the first ones to adopt Kubernetes. And now others are looking at us and they're deploying their own Kubernetes clusters.
That's awesome. And this environment is different than like a typical, like these aren't web services necessarily, right? That you're not running, you know, scale out web services. These are HPC style, like, you know, high memory, high CPU usage.
It's not really. So for HPC, you normally require a certain number of nodes. Like usually HPC is MPI. So you need to say, okay, I need 10 nodes. You're guaranteed to have 10 nodes, and you run on all 10 all the time. This is, again, different. So we're running jobs, not services. And there is a like base job in Kubernetes. But normally, users just run decoupled jobs. So they say, okay, I want 100 jobs to run like machine learning for me. And they got scheduled eventually, they run. If node fails, they will run somewhere else. So it's not HPC, but this is batch job as opposite to service, yes. And we have 500 GPUs now, so it's mostly GPU machine learning.
And the benefit here, like you said, was each university can maintain and own their own cluster. So you don't need that centralized cluster provisioning sort of thing like Cluster API would give you. This is really about, hey, let's just let, you know, a researcher schedule a job and then it can land wherever it might need to based on, you know, whether the resources are available there or like a location or data. Are those kind of the thinking behind where it goes?
Exactly, yes. Yeah, so our big cluster, like there are some universities that don't have admins and they just want to run, to join their node and not care about administering it at all. So then they just join our cluster. But if they do have admin and they want to manage it, then yeah, we can federate and then our jobs can be outsourced to their cluster. So it's really flexible. Like some users don't even care where they run. They just throw a job and it can land in our cluster. In different universities, it can land somewhere else. The only thing they should think about is storage. But we are working with Adrian and others on solving that.
I guess that would be one of the critical things is where's my data, right? I mean, because you don't want to always pull that data. But I guess the other thing that enables you to do this is those high bandwidth links between the campuses, right? Because typically you wouldn't join a node from a state away into my cluster if I'm going over the internet or a slower VPN or something, right?
Yeah, that's really critical. So we have a bunch of monitoring, and we make sure that all nodes are well connected. So they are above 10 gigabit. They have jumbo frames on the hallway. Like if there are no jumbo frames, then we don't join this node until they fix it. And yeah, so and in our cluster, all nodes can mount our Ceph storage. And we have 4 Ceph clusters in our big cluster. So there is one across the whole California, one local to UCSD, one on East Coast, and one in Pacific region. But all users, if it's critical, users can say, okay, I want my workload close to this storage. But sometimes they just cache data locally, and then they train on this local data, and then they can run whenever, like where there are resources, and they still can mount our storage.
Cool. And I just want to call out, I mean, you're enforcing jumbo frames. That's like living the dream right there to me. I've wanted that at pretty much every job I've ever had. We're like, can't we just enable jumbo frames? And so I was like, it'll never work. We can't enforce it. No one's going to do it. But that's great that, you can get so much more bandwidth and, lower packet overhead by enabling that and forcing people like, hey, if you want to join, here's the bare minimum to be able to do this. That's cool.
Yeah, what's funny is that Kubernetes is actually enforcing this because of this overlay network. It completely breaks once it's not a jumbo frame. It's just not working. So we immediately know when something changes.
Is that overlay network something that's UCSD specific, or is that an open source project?
No, Kubernetes. We use Calico.
Calico, okay.
Is doing this packet encapsulation. And because it's expecting jumbo frames, this encapsulation doesn't work once it switches to like 1500.
Right. Once you encapsulate that a couple times, it's not going to go very far.
Yep.
That's really cool. So, Adrian, I mean, we're talking about this use case, how we're enabling that for the scientists or researchers. Basically, just like, I don't care, just run this job. I want it to go somewhere, and UCSD doesn't have to have a giant data center. They can do those peering and kind of run it all wherever they need to based on distributed storage and the network. So how does Admiralty, how does it do that? Like what's the actual fundamental pieces that kind of make that possible?
Oh yeah. So to make that possible, it's important to connect the clusters, and so there are different pieces for that. And so clusters need to be authenticate. Let me show you maybe a little diagram to show you how that.
And for anyone watching the stream, again, I recommend go watch the KubeCon talk. There is a lot of details there. There's a lot of backgrounds. We wanted this to be not just a repeat of that that recording. So we wanted to give some more information, ask your questions and kind of dig a little deeper into, what this actually means for using applications that distribute across multiple clusters.
Yeah. So Admiralty is a set of Kubernetes controllers that uses regular resources like pods and config maps and etc., but also custom resources. And the controllers talk to their own clusters Kubernetes API, but they also talk to other clusters Kubernetes APIs. And so there's the user needs to set up authentication between those controllers and remote Kubernetes APIs. There are various methods to do that. In AWS, you'd use IAM and there are ways to do that. You can also, with Admiralty Cloud, you can do it across clouds. I mean, I won't go into those details here. And then one of those controllers is actually a Kubernetes scheduler, like a custom scheduler. There's two of them. One is in charge of the pods created by the users via deployments or jobs or other resources. It's kind of agnostic to that. And then on the other side, in what we call target clusters, there's another scheduler that handles what we call delegate pods that are created by Admiralty to and those pods actually run the containers in the target clusters. So, I mean, this will probably get clearer when once I jump into the demo. I don't know if we're ready to do that, or do you want to discuss more?
No, I mean, yeah, you can go ahead and show us like some of the pieces here on like how those nodes connect and everything else you have for a demo. We can ask questions as we go and kind of
let's jump right into the demo. Like that gets and then I can pull in some diagrams that'll make it easier to understand. So so I've provisioned. So demo here is a little different than demo we showed at KubeCon. At KubeCon, it was a demo on UCSD's infrastructure, but this time because I'm preparing the demo, it's on EK on my AWS account. I run 4 EKS clusters, and then on my laptop I run a kind cluster that runs EKS distro.
Can you make your font a little bigger?
Sure. I've kind of forgot how to do this.
Control plus should zoom in still in code.
Yes. Is this big enough? So, so let me show you those clusters. So here I'm in the EKS console in this dev account. The 3 clusters to look at are the management cluster and these 2 clusters that are basically named after the region plus a number. The topology what I call the cluster topology that I created here is centralized because that fits other use cases that than the one Dmitry talked about. Like you might want to have a central control plane to manage your deployments across multiple clusters, so that from a CD, a deployment perspective, you don't necessarily care about specifying which cluster to deploy to. You just deploy to this main global API, and then the system takes care of running pods in other clusters depending on what cluster is available, where resources available in those clusters, if cluster is down, things like that. The system takes care of that. And in the other region, I have 2 other clusters. This is in Paris, and the main cluster and 2 satellite clusters are in Oregon.
Can you zoom that a little too?
Yeah.
Thanks.
Okay. So, and then I have this kind cluster that I called on-prem, and on-prem can mean a lot of things, like you all discussed in the previous episodes. So what I'm going to do, I want to show you here in the management cluster, the nodes. Okay, that's why. Let me refresh my session. I'm going to take this window.
Yeah, go ahead.
For a little.
Yeah, the multi-tab authentication would kill it if you go to different regions without doing incognito or a separate browser. So
yeah, so I'm using single sign-on, and that's great, but like the sessions really don't last very long. So 1 second.
And the local cluster you have you already joined that to like this centralized infrastructure, or that's?
Yeah, it's already joined. So there are different ways to join it. And so I won't go into too many details here. What I use is a tunnel that's provided by Admiralty Cloud. You could also, use other tunnels and other authentication methods. Admiralty Cloud just makes it simpler, and it's also what we built, so that's why I use it. So I was here. Sorry for the delay. And so in this management cluster, now we can see the nodes. Okay, here we are. And so the two nodes here at the bottom are like a managed node group that is part of the cluster when I create it. And that managed node group runs it runs Cert Manager, which is a dependency of Admiralty, and it runs the Admiralty controllers. And the other nodes that you see here are virtual nodes. This says instance type Fargate. It's actually, so how this is computed is because those virtual nodes that represent remote clusters have labels from the nodes in the remote clusters. And so if a label in that cluster has a unique value, then it's kind of bubbled up. So we kind of have a view of what unique labels there are in the remote clusters, which can help with scheduling. So we know that. So
if you click on one of those nodes, I'm actually curious now. Like, I'm assuming our new console doesn't know about Virtual Kubelet in most cases, right? So like, it's just saying, oh well, this is something that I don't know. It's not one of our instance types as a Virtual Kubelet. So I'm almost wondering if we can add that support. I want to open a ticket on the public roadmap to say, hey, if I have a Virtual Kubelet node, we should put in our console, this is a Virtual Kubelet node, so that users will know about that.
That would definitely be great. There's a label that for Virtual Kubelet nodes, so that'd be fairly straightforward, and it would be compatible with all providers of Virtual Kubelet. So Admiralty is what we call a Virtual Kubelet provider. Like in the early days, Fargate was also a Virtual Kubelet provider, and then just it was kind of it's not open source anymore. But Fargate kind of works the same way. It provisions a node that represents an EC2 instance that has been provisioned just for your pod. And so what we're doing with Admiralty and Fargate is kind of in inception. So we're in one cluster. We see virtual nodes that represent other clusters, and in those other clusters are nodes that represent Fargate. So
you're boiling down an entire cluster at a different location as inside this cluster as a Virtual Kubelet. So if I say schedule my pod to that node, which is the Virtual Kubelet node, it then sends it over to the other cluster.
Yeah, and actually, from the user's perspective, you don't necessarily select a node. You don't like target a specific virtual node. You give you give scheduling constraints that would work in the target cluster. And so, I mean, for Fargate, maybe it doesn't apply much because when you use Fargate, you don't use complex scheduling constraints that are not necessarily supported by Fargate. But in other cases, if you weren't using Fargate, you could use complex scheduling constraints, and Admiralty will ensure that the cluster that is selected can accommodate the pod that you create, even though the information is not available from the management cluster.
Right, and so Admiralty is looking at the actual constraints of the pod, which are standard Kubernetes labels based on from the pod itself, right?
So let me
go ahead. I wanted to differentiate. Like if we create a Fargate cluster that has a Fargate profile and it has a different webhook that'll look for a namespace, and the namespace is what actually sends things over to Fargate runtime. Which is different, even though the cluster here says this is Fargate's, there is no Fargate profile. There is no webhook that's now scheduling that over to Fargate for runtime. This is just straight pod scheduling constraints, and Admiralty picks up those labels to send it to different nodes, which are clusters. Is that right?
Yeah. So for Fargate, like we actually use a slightly modified algorithm than the standard Admiralty algorithm, because we cannot with Fargate, you cannot use a custom scheduler. Basically, Fargate is the scheduler. So Admiralty has to work with that scheduler. And if you look at the coupon talk where I explained the standard algorithm, where you have two Admiralty schedulers talking to each other via pod annotations to kind of orchestrate the two-step scheduling that looks ahead to make sure that pods can be scheduling remote clusters. With Fargate, we have a slightly different algorithm where pods are sent to clusters, and it's kind of to one cluster at a time. And if it doesn't work, which we can get feedback fairly quickly, and there's also a timeout feature, then another cluster is we try another cluster, and until we find one that can accommodate the pod. But what you can do also, like you said, is use labels in the source cluster to kind of have a smaller subset of clusters to look at. And most likely, though, if your labels are accurate enough at the overall level, at the cluster level, there won't be too many attempts, as we'll see. So I hope that wasn't too confusing. So okay, so what I'm going to do is
real quick. Also, Dimitri, your use case, all these additional clusters are in other data centers at other universities. You're not doing multi-cloud, whatever that means. It's your centralized scheduler in San Diego connects to all the other data centers, typically on-prem for those other customers, right?
No, they can. So it's based on namespaces, and if some users from other university want to like federate with other user from another university, they can do that for sure. And also, it's not only universities. Like sometimes we actually go to cloud if we need more GPUs or we need some beefy GPU that we don't have. We can definitely like scale out to Amazon and temporarily like use that.
Cool. So those are all just, and it's still, high bandwidth direct connects, and you're able just to join the same cluster if it's you expanding, or whatever university, if they have a direct connect or high bandwidth to.
If we, so that's the thing, like inside one cluster, we have high bandwidth, but between clusters, we don't have to have it. Because like the pod goes to this another cluster. And if there is storage in Amazon and pod runs in Amazon, and we just need to like schedule it and get some result back, then we don't like, we can go over 1500.
Right.
If we are not using storage from UCSD.
Right. Okay.
And Dimitri was talking about bursting out to the cloud to use GPUs. I've actually talked to somebody who was looking at Admiralty to the opposite. They want users to use the cloud to as a main gateway, a main API to schedule their workloads. But then because GPUs tend to be expensive and they have plenty of GPUs on site, they want the GPU workloads to actually be scheduled on-prem instead of in the cloud. So it was another interesting kind of like a reverse cloud bursting use case. Okay, so let's look at the deployments that I'm going to create here. So the use cases that I'm demonstrating is it is in like a microservice, an application that you want to be highly available, and you want to have low latency worldwide. So you deploy it in multiple regions, like Oregon and Paris in this case, and you have multiple replicas in each region spread over multiple clusters. So like if a cluster has a problem, if a region has a problem, you would also have a networking layer that can direct traffic to the right instances. So how we do that, we actually have two deployments that differ in their node selector here, where we select a region.
Make that a little bigger, if you could. Try to pinch to zoom in for me.
Well, without too much. Okay.
There you go.
So, and so how so Admiralty is enabled at different levels. So in the namespace, there's so the namespace is labeled to enable multi-cluster scheduling. The namespace also has a definition of targets, which targets are enabled in that, which other clusters are enabled in that namespace. And then at the pod level, you also enable Admiralty with this annotation, which means we elect this pod to be delegated to other clusters. And there are some like specific annotations here to work with Fargate. This no reservation is just a switch to the alternative algorithm for scheduling without a remote scheduler, to use the Fargate scheduler instead. And this tells us that we want to use the node selector here to select a virtual node instead of using it to select a regular node in the target cluster. So as you see, there are that's what I was trying to explain earlier. That was a little confusing. There are two levels of scheduling constraints: the scheduling constraint at the virtual node level and the scheduling constraint at the node level in the target cluster. And you can do both.
That's cool, because you don't lose the built-in Kubernetes topology scheduling constraints. You work with them, so you could say, okay, go to this cluster and then figure out what Kubernetes should be doing. That's cool.
Yeah. And so here, by default, Kubernetes spreads pods across matching nodes. And so we'll see here when we request 4 replicas, there'll actually be 2 replicas in each cluster by default. If you can also configure Kubernetes to pack rather than spread the pods. And this is just a hello world that responds with the node name that it's running on, which will tell us what region, because node names have in AWS have their region in their name. And the other one is just targeting Europe. So I've created those 2 deployments.
And you're deploying those locally in your kind cluster.
I'm actually I could I could have configured the kind cluster to be the main, but I actually have an EKS cluster that works as the main.
That was the one you showed earlier, has those other nodes in it. Okay.
Mm-hmm. And then so here what I'm just doing is looking at the pods in each cluster. I just train a kubectl get pods on each cluster, and so we see. So Fargate can take up to a minute to schedule a pod from experience, and so when I ran this the first time, you can see. So here are the pods in the management cluster. They're what we call proxy pods. They represent the remote pods, and their status is actually a copy of the actual pod that is in the target cluster. So we have all those 4 replicas per deployment. And now I'm looking at the pods in Europe. There's 2 in each cluster. They're currently pending because they're waiting for a Fargate instance. And same in Oregon. And I think it's been about a minute. So if I run this command again, oh, okay, we're catching it at a great time. So some of the containers are already running, some are creating containers, and this is all so we see that in the management cluster, but it's actually happening in the other clusters.
Right. That's interesting that the status gets relayed based on the virtual kubelet, right?
Yeah, it's that's one of the features if you can, of a virtual kubelet.
So in this case, those target clusters where the workloads are actually running, the kubelet reports back to the API server and says, hey, this container is running. Mm-hmm. Your virtual kubelet from the management cluster talks to that API server, looks at what that kubelet did, and then reports back its kubelet status into your management cluster.
Yeah, it's so So it's basically a if you want a pod to pod control loop, looking at statuses,
and so you can see globally what containers you're having, where they run, and what's based on that proxy to those other kubelets.
Yes, and so here I'm not showing any a GUI because people use different dashboards for Kubernetes. I'm just using the kube control, which is good enough. But yeah, if you use Brancher or any other GUI to see your workloads, you would see the statuses in the management cluster where Rancher is running. Rancher is probably a bad example because they have other ways to do multi-cluster, but like, it works with the Rancher GUI. Surprisingly, I do demos sometimes with Argo CD, and you can see the Argo deployment running in Argo CD in real time, and so that's really nice.
And Dimitri, in your use case, is everyone submitting to a centralized cluster jobs and then they go out, or do they submit locally in their own clusters and then it gets rescheduled?
No, normally they submit to our cluster because we have authentication system based on CI logon. So that's OpenID, which is aggregating all the universities. And basically they're coming with their university's account to our cluster. And then they can schedule. And also we're providing help with like teaching them how to run stuff. Like we provide some containers for them with scientific software. So they're interested to go through our cluster because of the support we have.
And that simplifies a lot of their setup, right? Because they don't need to run, everything for the control plane for Admiralty inside of their clusters. I mean, they join the cluster, but otherwise everything submits to you.
Yeah.
Do they even, I guess they have the API server so that all the control loops work, and they have to expose that to you, but I guess they don't even need local access to that if they don't want people to, poke at the cluster locally. They really only need to expose that to your cluster to be able to schedule jobs, right?
Yes, and what's great is that they don't even need, like, if there is some admin controlling the cluster, but user has only admin in the namespace, they can federate their namespace without even talking to admin.
Interesting.
That's cool. If admin enabled like Admiralty in general, they can create credentials in their namespace, and so they are. Sometimes I don't even know what's happening in my cluster, as long as like nobody is, I don't know, mining bitcoins. I'm fine with that. Like they're running some workflows, they're collaborating, and they don't bug me about that. So they can fully control those like same level links between the clusters.
That's cool.
And it's up to the cluster admin to enforce the policies.
Got it.
Yeah, that's a good point. The target clusters like are in charge of their own role-based access control, and so you can allow you can allow source clusters to do this or that and this or that, or in different namespaces, and you're in control when you use Admiralty in a decentralized topology.
Yeah. And
so the next step of the demo is to show that services and ingresses follow the pods that they target, and so the next thing I'm going to create and apply is this manifest of one service and one ingress. And so this time it's not two services or two. I had two deployments, right? One for each region because I need a different node selector. But I can have a global service that will match all the pods, and a global ingress that will also match all the pods. And so I've deployed the ALB ingress controller in the EKS clusters that are connected to the management cluster, not in the kind cluster because that wouldn't work, but the pods of this deployment are not running in kind. I'll run a job in kind if we have time a little later. And so this is to be interfacing with this host. This is like an address under Admiralty Cloud, but you basically what will happen, you'll have ingresses in the other clusters, and each will have its individual your address, like hostname created by ALB, right? But they'll be different. They'll be in different regions, and so you need to somehow link them together. And so in AWS, you can do that in two different ways. You can either use Route 53 with some policies to direct traffic using latency and weighted records, so that latency-based and weighted records, so that traffic on the main endpoint would arrive to the ALB endpoints and to your service. Or you can use something like Global Accelerator. And so you can do that on your own, though it's a lot of plumbing. And Admiralty Cloud does the Route 53 under the hood. And then Admiralty Enterprise does Global Accelerator. I won't show that today. But I can just create those services and ingresses and show you. This is what I'll do also in open source, which is to go to the other clusters.
So you have your management cluster, the two other clusters where workloads are running. You're going to deploy this service. Each of those clusters has the ALB or the load balancer controller running, which is going to create an ALB, and then those all get pointed back to a centralized place, which creates one endpoint that then can route to the other places.
Mm-hmm.
Cool.
Okay, so I've created those. And the next command is to look at service and ingress in the different clusters. So you see in the management cluster, there's no address for the ingress because the ALB ingress controller is not deployed in that main global API cluster, but it's deployed in the other clusters and creates addresses for the ingress objects. So it's also been deployed in the on-prem cluster, but there's no ALB ingress controller there, so they're not used.
So if you locally in kind list your services, you'll see this service.
Yeah, this is what I did here. So basically what I run here is kubectl get service hello world, and before that I exported a kubeconfig, the kubeconfig variable to point at each cluster in a loop. And so kubeconfig on-prem targets my local on-prem cluster. And yeah, and so we see in here in the, we have this endpoint that we wanted to create, and so if I call it, okay. So what do I see here? Hello, and this is written from. It should have been hello from Fargate in US West 2 because I'm in Seattle, so I'm closer to US West 2. But if you're watching and you're in Europe, you'll probably hit, if you call this endpoint hello world. So this is my just user ID in Admiralty Cloud. You'll find another endpoint, and actually I can show the performance in different regions. Is this little tool to test the URL and see the latency. It's usually a little faster. Let me reload the page. Okay, so we see that we had two deployments, one in Oregon, the other one in Europe. And so as you can see, you get a good latency in Frankfurt and a good latency in San Francisco. In Asia, you don't get so good of a latency.
Can you go a little bit bigger on that? And also, I think I mistyped the endpoint. I was trying to curl it, and I'm not getting it. I think I got your username wrong.
It's H9LF2 after user dash. H9LF2.
I got some extra letters. That's fun.
Yeah, so we only have 15 minutes left, and there are a few things I could show, but I don't have time to show everything. So let me. So what we could do is we could scale down one of the two deployments and see that there's a failover to the other region. Or what we can do is we can also like drain a virtual node, and that's like draining a cluster basically. If we drain one cluster, then pods will be scheduled to the other one. So that's another interesting feature. Also, I could run a job that goes to my on-prem cluster from the management cluster. So we could go through those examples if you'd like.
So,
we can also I can also answer questions.
So if I wanted to, I need to drain a cluster for maintenance. Inside of this use case, it's literally just you cordon the node, and that automatically will start draining it. And what happens to that if I said I wanted everything to go to EU, West, but then I cordon that cluster? Do those get rescheduled, or do they just go back in the queue and wait for it to come back?
So they when you cordon, actually you drain it so that you also evict the pods. A virtual node, then the pods will be evicted, and the deployment or the replica set will create new pods to replace those pods. And then the scheduling will see that the node that you drained is cordoned, so you cannot schedule to it. So it will schedule all the replicas to the other cluster. And so
it automatically will pick another cluster for me.
Yeah. So for example, here I've cordoned one of the two European clusters. I use kube-control drain, so that cordons the node and also evicts the pods. And new pods, so then they're evicted. And what we'll see is that, let me look at my command to look at all the pods to show you that new ones have been. Okay, so I'm looking at all my pods. So you see now from a management cluster, you see that some are pending here. Those are newly scheduled, and the other one, there are 6 others that are still running because they weren't affected. They were in other clusters. And now, so I've you see US West 3.0 is creating pods to replace the ones that were evicted from US 3.1. So you've taken US 3.1 offline, and you can work on it. Maybe there's an issue with the cluster, or you're not very confident in upgrading one of the system components, and you want to do a blue-green cluster upgrade. You do this,
and that's interesting as a not only like maintenance but also failure detections, because I am getting US West 2 as well, because I'm obviously here in California, so I'm getting that, but I'm noticing new IPs coming in. Will it actually ever fail if you cordon both of the EU clusters? Does it completely fail over to the US, or do they just leave those pending?
Yeah, so that's if I cordon both, then the pods will be pending because there is no matching cluster. But your deployment in the US will handle the traffic because of the DNS policies.
And hopefully at that point, in any cluster you're running, you have an autoscaler or something. So if it all of a sudden starts noticing, hey, by the time the global load balancer gets it's saying I only have one healthy endpoint, whatever cluster that is, it's going to start seeing more CPU or more traffic or whatever the case. So hopefully at that point, your autoscaler, adjusts to saying, okay, I need to scale up now.
Yeah. So there are two levels of autoscaling here, right? But you're talking about the autoscaler, the pod autoscaler, right?
Yeah.
So
in the case of Fargate, it's the pod autoscaler.
Yeah. So here you saw that when I coordinate one of the European clusters, the other cluster basically got the existing pods. So basically, we maintain the capacity. You don't have to wait for the autoscaler in one cluster to catch up because one cluster failed. Because all the pods, like your current level of pods, is automatically transferred. You don't have to wait for the autoscaler to catch up with the load. Now, if an entire deployment were to not, if an entire region, right, were to fail, which is more unlikely in this case, then okay, yeah, you would only have 4 pods in Europe, in the US or Europe, whichever other region has failed, and so they would need to catch up to handle traffic coming from the other region, but that's more unlikely.
Right, but I just love the fact that this isn't replacing anything we were doing before. I can still use my cluster autoscaler to scale up nodes. I can use my pod horizontal autoscaler to create more pods based on that load. And those all work at the cluster level in those regions. And Admiralty is able to make sure that your capacity based on, whatever your constraints are right now in the EU are still, at the capacity that you initially defined for. I need this many over in the EU so that EU, people can hit it properly. In the US, if you want, US West 1 and 2, it can essentially load balance between those two regions. Yeah.
It's so it's that's really at the core of the design principles of Admiralty, is to be as transparent as possible, work with existing APIs. And so from a user's perspective, it's kind of transparent. You don't necessarily have to know when you create your deployments or your service or ingress that Admiralty is actually scheduling those pods to other clusters from a developer's perspective, or somebody who created a manifest for an app to run on the infrastructure. There's nothing really specific apart from an adaptation here or there. That's true.
Yeah, that's really cool. It really makes those annotations seem so much more powerful to say, hey, this isn't just multi-nodes anymore. This is actually, cross clusters, and that's really powerful.
Thanks.
I don't think we have time for another demo. If there's any more questions, go ahead and throw them in the chat. But we just wanted to, say and this is, sorry, going back to Dimitri's use case is decentralized. This use case is centralized. So there's different ways of using these global clusters depending on how you're adding compute resources, whether you kind of own those clusters or nodes or maintain them or whatever the case may be. That's empowering for a developer. I just want my job to run somewhere. I just want my web service to be available at some points. I don't really care about the details necessarily, right?
Mm-hmm. Yeah,
there's a lot of flexibility, and you can mix and match all the options.
Yeah,
like you can have centralized and decentralized between the same clusters.
And those namespaces that you pointed out, where I can join just a namespace and administer that piece of it, is also powerful, because I could have the same cluster essentially joined multiple different ways, right? Depending on how that's cordoned from the namespace perspective of, oh, I only want my default namespace to be joined, but nothing else. That's really neat. So if there's no other questions, we can wrap up the stream. I definitely recommend, anyone interested, go check it out. Admiralty is open source. I don't know if we linked that GitHub repo already. I'm finding it.
I also noticed that you all have some episodes of Containers from the Couch in Japanese. There's also a recap in Japanese of our talk made by that happened at the Tokyo Kubernetes meetup. It was by Shingo Omura from Preferred Networks, and you can also maybe post the links to that if there are Japanese people in the audience.
Yeah, definitely. And one of the other DAs here at Amazon, Tori, runs all of our Japanese. I don't speak Japanese. I did take a class, but I'm not fluent. So one of those things I want to do, but absolutely I wonder if the Japanese stream would want to, see some of that as well. That'd be awesome. So, All right. Well, thanks for joining and showing us how it works, and Dimitri for letting us know about your use case. This was really cool just to be able to see how it all works together in actual like real world. Like someone, yeah, no, this isn't just like a GitHub repo that someone was looking at. Like you actually deployed it and are using it. That's cool.
Oh, thank you.
Thank you, Justin.
All right. Have a good one.